Good morning, all. I'm Divyanshi Divedi is here to discuss our research work on the topic identification of critical nodes using angio causality for strengthening network resilience in electrical distribution system. Other authors for the paper are D. Manish Reddy, Dr. Pradeep Kumar Yamula, and Dr. Mayukha Pal. The background and motivation for the work is in 2018, a major power disruption that took place in Puerto Rico has affected around 8 million customers because of the failure of a crucial power line. These are the instances of a cascading failure that occur when a critical component in electrical distribution faces disruption, which result in power outages for a large number of customers. To avoid such scenarios, identification of critical nodes and implementation of necessary preventive measures have proven beneficial in preventing cascading failure. Placing DRs at the identified critical node is a crucial precautionary measure that help in maintaining continuous power flow and enhances the resilience of the system. In this work, we introduces a novel data-driven analysis that can be integrated into digital substation for optimizing DR allocation and identification of critical nodes. For that, we have simulated standard IEEE 123 node feeder system and obtained the time series data of active power flow among all the nodes. Then perform the Granger causality between the system nodes and identify the correlation between the nodes. In the cases where the node has higher dependency on other nodes are considered as the critical nodes of the system because that can trigger the cascading failures in the electrical distribution system. The obtained critical nodes in the system were identified and selected for the integration of renewable energy sources for improving their self-sustainability. Our study further demonstrated the placement DR at identify critical nodes which improve the resilience of the system by calculation of system's percolation threshold. Here we have used Granger causality, referred to as G causality, for identification of critical nodes in electrical distribution system, which is a statistical technique that determines how the past value of one time series T2 could help for predicting the future values for another time series T1, such that T2 Granger causes T1. The model 1 equation is given here, T1 x T2x. To test if T1 Granger causes T2, we need to determine if any legs are statistically significant in our model. The value of n here is the model order representing the maximum leg integrated into our analysis to compute the Akai information criteria and Bayesian information criteria. For evaluating the resilience of electrical distribution system, percolation threshold is found to be suitable as a quantifiable measure for system resilience. It is a tool from complex network theory which help in identifying the phase transition of any network. Basically, it is calculated by first determining the percolation strength of the network, then evaluating the susceptibility, and then estimating the percolation threshold rho C at the point of maximum susceptibility. Here are the equation for percolation strength, which is being computed at various iterations till capital R, and then we have computed the susceptibility of the network. Wherever the susceptibility is maximum, that value is considered as the percolation threshold for the network. The flow of the proposed work is as follows, which include the application of Granger causality and identification of critical nodes, followed by the assessment of system resilience. For that, we have simulated real power for the nodes of IEEE 123 bus test feeder and then computed the Granger causality among the nodes. To perform the Granger causality among the nodes, we have performed data covariance stationary through first order differentiating and checked using ADF and KPSS test for input time series data. Then using AIC and BIC criteria, we have calculated the maximum number of legs. Then performed the time domain Granger causality and checked its performance using validation test, which has resulted in the time domain plot of Granger causality and identified the critical nodes. These critical nodes are the optimal location for DR allocation. Then we have integrated the DRs at these locations and then computed the percolation threshold to check the system resilience. The system resilience check is done in comparison to the system operating without integration of DRs to see how the system resilience got improved. Finally, which has given us a resilient and self-sufficient microgrids. This is a system diagram for IEEE 123 node test feeder, which is clustered using community detection clustering algorithm into two regions, region 1 and region 2. These regions are not topologically connected but are clustered based on their similarities in operation. For both the obtained region using community detection algorithm, we performed Granger causality to identify the critical nodes in both the regions. Here are the results for region 1, which shows that the node 5, 10, 13 and 15 are highly dependent and correlated nodes of the particular region. Thus consider them as critical nodes as a failure would result in system shutdown. To avoid these cascading failures, preventive measure, that is integration of DRs at these locations, is recommended. We have integrated solar PV panel at these locations, and it is clearly seen that the dependency between nodes have significantly dropped, and also the magnitude of dependency has dropped here as compared to the system operating without integration of DRs. Similarly, for region 2, we obtained nodes 2, 4, 5, and 6 as critical nodes because they have high dependency among all other nodes in the region 2. Then integration of solar PV panel has significantly dropped the dependency and correlation between the nodes. Here also we can see that the magnitude of dependency has dropped from 0.035 to 0.02, which is a significant drop in the magnitude. Then we have evaluated system resilience using quantifiable measure, that is percolation threshold, for both the region under various conditions for renewable integration. Generally, high value of percolation threshold represent the system to be more resilient. Here for region 1, we can see that without renewable energy sources, the percolation threshold value is 0.06722, which is further improved by random integration of renewable at some random nodes. Then we integrated same rating of renewable at identified critical nodes and observed a significant improvement in system resilience. Similarly, we performed the analysis for region 2 and found that the same inference as above. Thus, we can say that the integration of DRs at critical node obtained by the proposed method provide a self-sufficient and resilient electrical distribution system. Here I would like to conclude the work. The proposed methodology provides an effective approach for optimal DR allocation in electrical distribution grid and also quantify and validate the system resilience. For that, we have grouped the nodes of IEEE 123 test feeder system into two clusters based on similarity using a community detection algorithm. We further employed Granger causality to determine critical nodes in the system and then perform Granger causality again with solar PV integration at these locations and observe that there is a significant reduction in causal dependency between the nodes. Further, to validate the proposed method, we calculated the percolation threshold for both the region under two conditions, integrated DRs and absence of DRs. The result demonstrated a 31% of increase in percolation threshold for region 1 and 37% increase for region 2 when RES got integrated at these critical nodes. These findings have proven the effectiveness of our proposed methodology in developing a reliable and resilient distribution system with less node dependency, and node could maintain demand independently. Thank you all.